Okay, this week we're going to talk about air pressure. So I thought I'd start off with a surface pressure map. Now the central question this week is just understanding what air pressure is and how it changes and what impact that has on the weather. So if you look at a surface weather map, and you've analyzed them now several times, you're seeing isobars, which are pressure. You have a low pressure down over Oklahoma, another one up northeast of Chicago, and there's high pressure out here in the Rocky Mountain area right now. And there's also high pressure off the east coast of the United States. So why are these areas different pressures? And that really is the key to understanding a lot of what goes on in weather. Why is this area having high pressure, or this area, or why is this area low pressure? So let's start looking at that a little bit. So we'll go here. What is air pressure? It's a force. A force is like if you slammed your fist into something. When you hit it, you exerted a force on what you were hitting. Or if some air pressure in this case is a force from the atmosphere. Its mass, which is just made up of molecules of the air, times their acceleration. That acceleration can be up or down or sideways or whatever. Molecules have acceleration themselves due to kinetic energy. So the two combine together to provide weight. So that's a force. Dalton's law very simply says if I have any number of gases, each one has a separate weight, but the total pressure on that amount of gas is what each one of those individual gases exerts. So in the atmosphere, we have nitrogen, we have oxygen, we have water vapor as a gas, we have carbon dioxide. Each one of those exerts a different pressure. But the total is what showed up back on that surface weather map. So we define air pressure, just like I said, mass of molecules and the kinetic energy of those molecules. The average air pressure over the whole world is 1 kilogram per cubic centimeter, or 14.7 pounds per square inch. All right, how the heck do you stand up with that much weight on you? Well, guess what? Your body has air in it. Structures have air in it. So they exactly exert the same pressure upwards as is coming down. So that is why nothing collapses under the weight of the atmosphere. You can take measurements of air pressure with barometers. Used to do that, they were mercury barometers with a tube that had no air, nothing in it, that was just inserted into the mercury, and the mercury just pushed up that tube. And that would give you your inches of mercury. Many home barometers in the United States especially still read in inches of mercury. That's why if you tune on a TV meteorologist, look in your weather app, almost all the time they're going to report it in inches of mercury. So that is one fact. However, if I'm a meteorologist, I hate working in inches of mercury. The math equations get extremely more difficult. So I want to go to another unit, my unit millibars, which are exactly the same as literally kilopascals. They're a metric unit, really. So that is the unit of pressure I'm going to typically refer to. And you can here relate them to inches of mercury if you want. But basically, around 1,000 millibars, 1,004 millibars is about the same as 29.97 inches. So that would be about the normal atmospheric pressure. So it's below that, it's going to be tending towards low pressure. It's going to be above that, it's going to be tending towards high pressure typically. So, and air pressure is interesting. The atmosphere is a fluid, like water, but you can't compress it. It is compressible. Water, if you try to squeeze it between your hands, it's going to come out somewhere. Actually, if you tried to squeeze air pressure in your hands, it's not necessarily going to come out. If you can make a tight enough seal, you're going to hold that air pressure in. So what does that mean? Well, air is compressible, so therefore the weight of the air will change very rapidly in the vertical. Now, if you have the ocean, it's not quite so fast. Yeah, the ocean is going to get heavier and heavier as you go down, but it's not compressing. It's just the weight of the water above you. Here, because the air has been pushed down towards the surface of the earth and compressed, as you go higher on the mountaintops or go up it, your pressure is going to drop significantly. And it's going to drop much faster in the lower part of the atmosphere than in the upper part of the atmosphere. Horizontal pressure variations. Say a low pressure was moving by your house. You can see here they dipped down, lower, back up. So this would be the low pressure approaching, low pressure leaving, and high pressure moving in this area. So that is a typical pressure change that many of you see at your house or anywhere around the country. So if you have rising air pressure, you're increasing kinetic energy in the molecules. Now, we've just talked about this. The atmosphere is not a closed container. So what happens, the hotter the air pressure, the air temperature, and we just talked about temperature, you're going to push those molecules further apart because they're hitting each other faster, which is going to cause them to have lower density and not weigh as much. So the warmer the air, the lower the air pressure, typically. That's one of the things that happens. And if I was to go back and look at this weather map, notice this low pressure down here in Mexico. That low pressure is actually being caused by heat from the sun. Temperatures, there's a ridge there that gets very, very hot. That low pressure, very dry, but typically very, very hot. So it is pulling in and dropping the pressure because of the sun. Not all low pressures work that way, but some do. And you'll see it out in the desert southwest as well sometimes. You'll notice there's several low pressures here along the desert. These are due to very intense heating, and they'll become more pronounced later in the day today as the sun continues to shine out there. There are other things that change air pressure. One of the things about the atmosphere, we talked about it being a fluid. So if I push winds towards each other, like your palm of your hand, that air is going to tend to either go up or down, depending on whether I did it at the bottom of the atmosphere or at the top of the atmosphere. The higher up, if I push winds together, the air is going to want to sink. If it's sinking, it's accelerating downward, so it's adding to air pressure. The air pressure would tend to be higher. If, on the other hand, I had that same convergence occurring at the surface, now it can't go into the ground, the air, so it's going to tend to rise. If I'm pushing the air up, I have lower air pressure. So now you've just noticed winds converging and winds diverging. The gas law, we're going to talk about that in this chapter. There's three variables: pressure, temperature, and density. Think of density as being the number of molecules in a certain area. So the more molecules in that area, the denser the air is. Well, we just learned that the molecules tend to push apart in air when they're hot. So the density is going to be lower when the air is hotter. The density will be higher when the air is colder. So in very cold air masses, all the molecules are tightly packed. You're going to have much higher density. So if the density is higher, that relates to the pressure and temperature. depending on how they change. If the density is held constant, then if you know the temperature, you can know the pressure. So all these variables are related. There are some things that force temperatures to change. So as we let air out of a tire, if you ever feel the air coming out of the tire, it's quite cool. That's because the air is expanding very quickly. That's expansional cooling. So if the air is expanding, it's cooled. The air is doing work. If it's doing work, it's losing energy, it's cooling. Now, if the air is being pushed together, say you have converging winds pushing the air together, then the atmosphere is doing work on that air. So it actually is going to warm up a little bit, if that is where the only factor involved. And if you pump air into a tire, boy, those pumps can get really hot, especially if you're doing it manually like a regular tire on a bicycle. All right, so if you know that the air temperature and the pressure are changing, you can actually calculate something called the dry adiabatic lapse rate. And all this is, if the air is dry, this is how much the air will cool. So we're going to talk about air parcels a lot in the weeks ahead. An air parcel is very simply any size parcel of air you want. Say it be 50 feet across, say it be a mile across, and that air parcel, as it goes up, the density around it is going to begin to lower. It's going to tend to pull the parcel apart, and as the parcel is spreading, what is happening to the temperature? Well, the air is doing work to spread the parcel apart, so the temperature is going to drop. And wonderful person calculated it for us. In 1,000 meters, it's going to drop 9.8 degrees Celsius. Or in 1,000 feet, it's going to drop 5.5 degrees Fahrenheit. So as you climb a mountain, that's why it gets cooler the further you go up. And remember, this is dry air. We're not bringing anything with moisture into this right now at all. However, moisture changes things. And we will talk about that more next week. But actually, moisture, because we learned last week, moisture releases latent heat. So if the moisture is condensing into a cloud, latent heat is being released, so that air parcel can't cool at the rate it was just cooling. So I want to look at a couple more things here. I wanted to look at a vertical picture, since we're talking about the vertical. And here is the temperatures out in Seattle, Washington. One of the interesting things, this is early in the morning. So infrared radiation has cooled the lower part of the atmosphere, but hasn't cooled all the way up in the atmosphere. So this is really a quite warm sounding. Notice it's 30 degrees Celsius right here. And this is a 950 millibars, say about 1,000 feet up. So if I was to warm to a dry adiabatic lapse rate, which is this line right here, I warm dry adiabatically, I get almost up to a 40 degrees Celsius. That's a good approximation of what may be the maximum temperature today. If you warm that lower atmosphere, it's going to tend to go towards dry adiabatic, and that's going to give you your maximum temperature. Upwards, you can see the temperature never drops at a true dry adiabatic lapse rate. It cools, but it never quite cools at dry adiabatic. You almost never see that because the air mixes too much. The same thing if you looked here at Fort Worth down in Texas. Here, it doesn't cool anywhere near dry adiabatic because you got lots of moisture down here. So you're getting the latent heating in there and other aspects as well. Finally, just looking at aloft, we talked about high pressure. At the surface, we talked about big high out in the Midwest. Here's where the high pressure is aloft, right over Seattle, and into Portland, Oregon. These are all contours on this map, and they just demonstrate a solid line how this is higher contours for 500 millibars, so it's further away from the surface. These are lower contours, so they're closer to the surface. They represent ridge, trough, high, low. They're not exactly aligned up with at the surface, but they give you a good representation. So just wanted you to get some feel for pressure here. So if you have any questions about this section, please don't hesitate to ask.